Okay? Any question? I hope you are doing the assignment. Any difficulty? Yes. So there is no change in the definition of the DB or MC which you have used in the previous semester and this semester. Both are same. Only thing is you have to understand that in force-based design, we design for DB. And what we do, we first calculate AH. Then we calculate base shear. Then we calculate factor base shear, that is 1.5 into 3. Okay. Because load factor is 1.5. In displacement based design or performance based design, we can determine performance at DB, SE, or MC. So MC we are taking as 1.5 into Z into SE by Z. DB we are taking 1.5 into Z by 2, and SE, okay, we are taking as where is the discrepancy? Only thing is that previously you were considering I by R. We will consider this I by R explicitly in displacement cases. So if you take I by R is equal to 1, this and this are same. There we were multiplying 1.5 into the load factor. This we were doing a load combination. Here we are taking this into account here.
But here sir, you are for getting yield base shear, we are dividing by whole strength factor also.
Yield base shear is different. This is design which is coming from earthquake. Okay. Yield base shear is of the structure. Whatever way you design, yield base shear is that of the structure. It has nothing to do with the earthquake. The structure you have designed somehow. And then you are plotting base shear versus delta roof. Then this is your V1. Okay. Now how you have designed this building, this is a different. So you can design in many ways. You can design based on your dream. Okay. Whatever way you have designed it, Vy will depend upon that. Suppose you have designed it as per code, then this base shear which we have calculated here, this one, this base shear will be here. Only if you have designed it as per code. If you have designed it differently than code, then this may be anywhere. And then this ratio is over. If you have designed, using force-based design method of code,
This base shear you are taking is only VB equal to H into W or 1.5 into H into W.
okay, you are right. It should be not this, but this is finally what you are designing for. So this into over strength, so this will be actually 1.5. Finally you have designed for this. You have not designed it for VB, you have designed it for 1.5 VB.
Force-based design will be always designed for dB as well.
Yes. All the codes of the world, they design for dB and assume that when NC will come, our building will not collapse. This is an assumption. It may be true, it may not be true.
We can also design for MC,
We can design for MC as well, but then the forces will be double. So, if you want to design for double the forces, you can design it. But why will you design for double the forces?
Because my demand is also,
Demand is also,
demand can be anything first of all.
demand can be anything, yes. So, if code says that you can design for dB, and if you are designing for dB, your building will not collapse under MC. So why you will like to design it for dB, not for, sorry, MC, not for dB, double the force. Double the force means more money. So why you want to spend more money? Why? You don't want now? Because you have to pay money? But you can still pay, because you may not like that your building should reach at the verge of collapse, and in some cases even collapse. Because code-based method, where does it ensure that the building will not collapse under MC? Have you made any check at MC which shows you that under MC it will not collapse? Have you done any check in code-based method? No. It is just in good faith that you do like this, it will not collapse. Okay, but nobody has checked it. If you check it, then you will find that actually it is not true in all the cases. In some cases, your buildings are going to collapse. That has been recognized by ASC 7, and in ASC 7 now the risk has been changed. Earlier they were considering 2/3 of MCE. They were considering. In place of Z/2, okay, they were considering 2/3 Z. First of all, why they are considering 2/3 Z and we are considering Z/2? Because the relationship between dB and MC is not constant. It varies from place to place. Okay. So within America itself, they have studied and they have found that not in all the cities dB is 2/3 of MC. It varies from half to 2/3. Okay. So they are considering dB as 2/3. Now they have changed it to 2/3 of MCER. What is this R? This is risk target. What is risk targeted hazard? 10% collapse, condition to occurrence of MCE. So if MC occurs, 10% buildings will collapse, which will be in MC. Now in any earthquake, even if MC is occurring, MC will occur in a small area, not in the whole area. So where MC, whichever region MC or higher shaking is occurring, 10% buildings may collapse. So they accept 10% buildings to collapse. Okay. Again, they have only changed MCE to R, but the design procedure, it will not depend only on hazard what you are considering. It will depend upon the design procedure also. So still, it is not confirmed that if you design for this MCR, you will achieve 10%. Okay, because that will depend upon the design procedure also. And design procedure in ASC7 is also force-based design. And in force-based design, you are using a response reduction factor R. And they use for ductile buildings, they use a response reduction factor of 8. What we use as 5, they use 8. So you can imagine how big a gap is here. One country is saying that we can reduce the forces to 1/8. Another country is saying all other requirements are same. Design procedure is same. If you see our code, design code as well as detailing code, it is exactly same as American. But they take a response reduction factor of 8, we take a response reduction factor of 5. Okay, understanding that actually 8 is too much. Then Eurocode, even less response reduction factor. So there is a lot of uncertainty about this response reduction factor. That's why force-based design does not even ensure what it promises. It promises, our code says, without saying, it doesn't say anything actually now, that has been removed. But understanding is this, common people understand, if you design as per code, nothing will happen. Engineers understand, if you design as per code, building will get damaged, but it will not collapse. Actually code does not even ensure that. That's why we have done whole of this semester. So using performance-based design only, you can ensure that whether your building is going to collapse or it is not going to collapse. Okay, or it is going to be I or it is going to be LS. But here also one catch. What is that? We have not considered uncertainties. We are using a deterministic method. So when you will consider uncertainties, then you will be able to calculate the collapse probability. So we can do what we call risk targeted or risk-based design. In risk-based design, we consider the probability of occurrence of different intensity of earthquake, okay, and also the probability of our building getting collapsed. Okay, so using this method, what we have discussed, you can calculate collapse capacity, and you can calculate variance. And assume a log normal have studied normal distribution. We have studied. Okay. What is normal distribution? Normal distribution is like this. Here is the mean value, and then you have sigma. Okay, 84%. This is normal distribution. If you plot normal distribution of the log values, okay, this will become log normal, and in that case it will be like this. It will be skewed. Okay, so this is the mean value. So mean capacity, let us say SA bar. What is SA bar? The spectral acceleration or spectral displacement at which my building is having collapse. Collapse prevention performance level is exceeded. So that is the mean value, and then we can get the variance of this, which we call beta, and this distribution what we call probability density function or probability density distribution. From this you have obtained cumulative probability distribution, not probability density but probability distribution. Okay, I have not written here anything, so this is, let us say, S, and this is the probability of occurrence line. Okay. Then you can plot this probability distribution. Probability distribution is like this. It is integral of that. Probability distribution is integral of probability density. Okay. So the maximum value will be asymptotic to 1 and the minimum value will be asymptotic to 0. Okay. And this is the probability. Here this will be 50% probability and the corresponding value will be SA or SD bar, whatever we have plotted this. So we get the mean value from analysis, we get the distribution, then we can plot this function. Okay, this is called the fragility. So fragility function is giving you the probability of collapse, let us say, or probability of IO or probability of LS with SA. So as the value of SA is less, the probability is also less, and as SA is increasing and at some value of SA, okay, if you go on increasing the spectral acceleration, at some value all your buildings will collapse. So that's why this probability is 1, the maximum value, but this will occur at large value of SA. So this distribution we get, which we call fragility function, it is giving us the probability of occurrence of a particular damage state. The damage state may be IO, LS, CP, collapse. Okay. So any of those, or sometimes people also define the damage state in terms of grade of damage. Grade 1 damage, grade 2 damage, grade 3 damage, grade 4 damage, grade 5 damage. Okay. Sometimes they define this in terms of indices. So energy based indices are there, that when the structure will dissipate full energy of its capacity, this will be 1, and depending on how much energy it has dissipated out of its total capacity, they can define indices. So like that, number of ways in which we can define the fragility function. Okay. Here we are defining the fragility function in terms of SA, the mean value at which the probability of collapse is 50%. So what you are getting from your deterministic analysis, it is actually mean value. Okay. So still there is a possibility of damage even at lower value of SA. You have calculated the capacity of your building at a particular SA. Okay. But in some cases, if you consider uncertainty, because the concrete strength may be slightly lower, the reinforcement you have put may not be exactly the way you have considered. Earthquake spectral shape may change. SA is same, but the spectral shape has changed of earthquake. It is not the same shape which you have got. So all these can result collapse of the building even at lower values of SA. That is given by this fragility function. Okay. What we do, we combine the hazard function. What is hazard function? Hazard function is giving the probability of occurrence of a SA. So what will be the shape? The shape will be like this. Larger probability, smaller value of SA. Larger SA, smaller probability of occurrence. So this is SA. It is also lambda versus SA. Fragility function also we have plotted lambda versus SA. So this is probability of occurrence of any value of SA, and this is the probability of failure at that SA. So what will be the total probability of collapse? At any value of SA, suppose there is probability of occurring of 0.3 G SA is 30%. Similarly, the probability of collapse at that value of 0.3 G is, let us say, 50%. So what is the probability of collapse of the structure? Multiplication of the two. So if you multiply these two and integrate over the whole area, okay, that will give you total collapse probability in a given time. And what will be that given time? That given time will be this, will depend upon this lambda. Whether this lambda is defined for 50 years, so much probability in 50 years, or so much probability in 1 year. So it is either annual probability we take, or during lifetime. That means 50 years. So acceptable probability of collapse as per ASC 7 in 50 for normal buildings. This is the acceptable probability of collapse. That means during the lifespan of all buildings in the country, okay, 2% buildings may collapse due to some earthquake or other. All buildings will not be subjected to same earthquake. Buildings will be subjected to different earthquakes. Buildings have been constructed differently. Their objective is to achieve this, that not more than 2% buildings should collapse due to earthquake in their lifespan. In whole lifespan of 50 years, suppose there are 1 million buildings in the country, then not more than 2% of that 1 million, okay, those buildings should collapse during earthquake. So that is the target. This targeting this risk they are developing their code. We are yet to reach at this stage. We are trying to achieve the performance basis. So at least the deterministic value, the median value, we should be able to achieve IOLSC. Okay. So this is the next generation of performance based design. We are not yet considering it. We are not taking the details of this also to you, but you can consider, and maybe when we develop a PhD course, there perhaps we will talk about it.
Sir, let us suppose we have this target X, that is 2% in 50 years.
Right.
What are the steps that
It is iterated. It is iterated. That's the problem. So suppose you want to design your building for this 2%, then you have to design for MCER to have 10% probability of collapse. You recall? This acceptable risk is 10% condition to occurrence of MCE and 2% for occurrence of all earthquakes. Earthquake less than MCE will also occur. Earthquake more than MCE will also occur during the lifespan of the structure. So if you take all the occurrences and take the corresponding probability of collapse and add those, that is 2%. Because occurrence of MC itself is less. How much is occurrence, probability of occurrence of MC? MC 2%. So 2% in 50 years is the occurrence, possibility of occurrence of MC. Okay. And 10% is the probability of collapse at MC. So what is the probability of collapse due to MC? 2%, that is 0.02 into 0.01. So 0.002. Okay, 0.2%. So 0.2% due to MC earthquake. But only MC earthquake is not going to occur. Earthquakes lower than that can also cause collapse because of uncertainties. Earthquakes larger than that can also occur, although even less than 2% probability. So if you take effect, cumulative effect of all those earthquakes which can occur during the lifespan of the structure and multiply with the corresponding probability of collapse, then that should be less than 2%. Okay. Alright, so can you now tell me this question, answer to this question? If you want to design your building for this, what should you do? First of all, you have to get a hazard cut. Just knowing DBMC will not work, because DBMC are only 2 points on this hazard curve corresponding to, let me use another one. This is, let us say, 2% probability of occurrence, and no, other way around. This is 10%, let us say, and this is 2%. So this is DB and this is MC. So only two values we need. Actually, we need the whole curve. So if we have to do the design, risk-based design, first of all, at my site, I should not know only DB and MC hazard. I should know the full hazard, probability of occurrence of all levels of earthquake. Okay, so I will develop this hazard. Then I will design a building. Okay,
as per any
method, maybe using our DDPD, which we discussed. You will decide that suppose I want to design collapse prevention level. So for collapse prevention, you will design a building. Then after designing that building, you will calculate its median capacity. How you will get median capacity? The way we have done. Either non-linear static procedure, okay, Okay, so you have got this SDU. Corresponding to this SDU, you calculate SA. At which value of SA? This is the SA of the earthquake. Okay, after reducing, this curve will intersect this one. The maximum earthquake this building can register before collapse. So that is at the maximum value of displacement, maximum ductility capacity. It has, if you utilize the full ductility capacity, then what value of earthquake in terms of SA it can register? That is its capacity in terms of SA. Do you agree? You understand?
And that will be the meaning.
This is using linear, static, non-linear. Using dynamic method, what you will do? Other alternative is perform a time speed analysis, take a ground motion, go on increasing this ground motion, scale up this ground motion, and plot the SA of the ground motion at the period of the building versus its roof displacement or SD. If I go on increasing the SA, what will happen to the building? At some value of SA, some hinges will form. So I will get a curve like this, and at certain value of SA, it will collapse. Okay. When it will collapse, what will happen? Suddenly its displacement will increase significantly. So you will get curve like this. This is called dynamic capacity curve. And this method is called incremental dynamic analysis, IDA. Incremental because we are increasing, gradually increasing the intensity of the ground motion. This will give us the capacity. So there is a difference. Here this point was not giving us the capacity. This is not the capacity. This is SAY at which it is yielding. You have to keep in mind. This is only SAY. It is not the capacity. Capacity is if you extend this to here, okay, then this is your capacity. This much earthquake, okay, because after reduction, this intersects just at the ultimate point. Okay, so this original graph, original response spectrum without reduction, that is the capacity. That will be the actual earthquake which this building can register at collapse. And this point where the curve becomes flat, this is only SAY. Whereas here, yielding is occurring somewhere here when the hinges are formed. Okay, this point is giving us the collapse capacity. So we will take this as the collapse capacity. But this is again mean value of the collapse capacity. Either you obtain like this or here. You have to consider variability, uncertainty in this value also. How you can do variability? How you can get variability in the value? Capacity we have obtained from the model. Okay. Suppose two people make different models. Will the collapse capacity be same? Will it come out to be same? Suppose one person has used lump plasticity model, another person has used fiber link model. Will the capacity be same? No. Okay. Then the actual building which will be constructed, the properties of the material there and the properties of the material which you have considered in your model, are those going to be the same? No. Okay. The ground motion which I have considered here, will the ground motion which will come At your side we say no. So all these are uncertainties. Those uncertainties you will use to calculate beta. So it consists of beta modeling, beta record to record variability, RTR. It consists of beta capacity. So different sources of uncertainty, when you will add, that will give you the beta. Okay. For adding this, we can use some sort of simulation, Monte Carlo simulation or some other simulation we can do. So obtaining this beta is a more difficult part than obtaining median capacity. So generally what we do, beta we obtain from past studies. Assuming that the variability will remain more or less same. Okay. Due to variation of the concrete properties, due to variation of the steel properties, that limit in which this can vary, that will remain same. So this we obtain from past studies. Median values we obtain from our analysis, either IDA or static nonlinear. Okay, that will give us the median capacity. Then we will develop fragility curve. Then the hazard curve which we have obtained and this fragility curve we will integrate and see the collapse probability. If it comes out to be 2% or less, it is okay. If it comes out to be more than 2%, then what we will have to do? We have to reduce. We can't reduce hazard. Hazard is coming from the side. We can only alter fragility curve. If I have to reduce the capacity, reduce the total collapse probability, how I should, in which direction I should alter my fragility curve? I have to reduce it. How can I reduce it? I can reduce it if the curve has higher strength. You can see that at 50%, no, 50% was not this, 50% was yellow. This was 50%. At 50%, this value has to be high. You can see that it has increased. So you have to design it for larger ratio. To design it for larger ratio, repeat the process again. Right. That is the risk targeted math. You will be happy to know this is not in your syllabus. Okay, it is only for your interest. Okay.
So it means that this is the most rigorous method till now.
So this is the most rigorous method till now, which considers not only the non-linear behavior of the structure, but also uncertainties involved in the whole process. Okay. So this is probabilistic framework of performance-based design or risk-targeted method.
And the biggest shortcoming is that beta part.
But it's not shortcoming, the challenging part. Okay, you have to put lot of effort in obtaining this beta. You can obtain beta yourself. Okay, this beta you can obtain yourself, but it will require lot of computation. Our designers do not want to do nonlinear analysis of a single building. Here what you have to do? Is anybody aware of Monte Carlo simulation? What we have to do in Monte Carlo simulation? We have to develop different models, okay, large number of models considering different values of these parameters. So you have to only do incremental dynamic analysis of a few thousand buildings. That's it. So doing nonlinear analysis of one building is a task. Doing nonlinear analysis of a few thousands samples of that building, that's the biggest challenge. Okay, so that's why people are working on quantifying this beta. And I can tell you, at the till moment, very few studies are there even on beta. This is a good PhD problem. So if you can do this analysis for, let us say, Indian buildings, okay, and come out with the value of beta, that will be a big contribution. Because this beta, when designer will be designing the building in design office, he can't do thousands of nonlinear analysis. So beta has to be taken from certain guidelines, certain pre-defined values. Okay, so those predefined values have to be obtained from research. Once those values will be there, then one nonlinear analysis they can do to get the median value, median collapse capacity, and then what else they can do. And even there also they have to do vibration. So if you want to do a more reliable analysis, the easiest thing is that you listen to the wise people sitting in the code committee. They have given you a very simple method. Divide this by R, perform the analysis and forget. Only see when the earthquake will occur. What else? That is easiest method. Life is most easy. Then came pushover. That you do pushover, calculate the capacity. People were very happy. Okay. In 2001, when I started studying earthquake engineering. Before 2001, I have not studied any earthquake. So 2001, when I started studying earthquake engineering, FEMA 273 and ATC 40 documents have come, and anybody who learned that used to think that he is boss. So there was so much hype about pushover analysis. So much papers you will find. If you learn, if you know how to do pushover analysis, you will great. Then people learn that no, it's useless. Then they started doing time history analysis, incremental dynamic. Okay. Then incremental dynamic analysis, lot of problems still people are struggling to do incremental dynamic analysis. It is not yet over. But then they discovered that no, that is also not sufficient. You have to go far. So still it is continuing. We will keep moving in that direction. Okay, we will improve every day. So whatever you will do, it will be a small contribution in that direction. But that's where currently the research front is. Some way you have to contribute into this. Okay. Any question after this point? Yes.
So can you please explain that capacity of structure in linear analysis?
Linear.
Static analysis.
Non-linear static analysis. Here.
You just said if we go for that original response spectrum. What is that?
So this is the maximum displacement my structure can resist. Okay. And corresponding to this, I can calculate the response spectrum which will give me this displacement. Okay. So what I have to do? I have to consider the energy dissipation which is taking place at this level.
Yes.
So that will give me xi equivalent. This xi equivalent I will calculate R xi. I will reduce that response spectrum by R xi. And that response spectrum should give me performance point. If my performance point reaches this point, that means I have reached the collapse. This is my collapse capacity. So that earthquake which is giving me performance point at this point, ultimate point, that is the capacity. That earthquake is defining the capacity. How to define the earthquake? Either PGA or SA, usually, or SD. We usually define in terms of SA. And how do we define SA? That this is the period of the structure. We extend this value of SA. This is defining the intensity of the earthquake. When we are using response spectrum to represent that, in that case, it will be defined by SAT. This is capacity. Capacity means what? That the largest earthquake which my structure can survive without collapse. That is the capacity.
So that is demand plus that.
Yeah.
So
Demand and when demand and capacity match, that is performance point. So at this performance point, this demand is matching with the maximum capacity of my structure. So this demand is the capacity of my structure. How you will define demand? Suppose you want to define a strength of a beam. How you will define? The maximum load it can resist. So demand is always, capacity is always defined in terms of demand. Maximum demand it can resist, it can take. So in the same way, in case of earthquake, what is the capacity? The largest earthquake it can resist. So the capacity will be always defined in terms of the maximum demand it can resist. So this is demand, but that demand which will give me performance point just at the end of the capacity. Okay. You may be confused that why we are not taking this as the capacity. Because if I take this as the capacity, then I am not considering the energy dissipation. So I have to consider the energy dissipation also, which will be happening. In that case, it will be considering only this value of SA, which is SAY, which this structure can resist even in elastic conditions. So I have to take the advantage of inelasticity also, and that is moving from here to here. Okay, think about it. It's relatively new idea for you, so you will take some time. But any other question you have?
Sir, there is confusion between the response reduction factor, load factor, overstrain factor. Because in the elastic design, you are reducing this base shear force by response reduction factor, so that the structure go into inelastic and is better by using stress system. Then again you are increasing that base shear by 1.1 factor. Here we are reducing that, and here we are increasing that. And again here on displacement based design, we want Vy, so that we can model that hinge for Vy. And again we are using this overstrain factor, and that overstrain factor is coming from characteristic strength, and actually is expected we are using capacity. So these are.
So what is the confusion? You have explained everything yourself.
Explain, but sir, these are interlinking and you are using that one.
So you are angry why they are using so many factors.
No sir. First we are decreasing, then we are increasing.
Yes, we are doing like that. You are right, we are doing like that. But what is your problem? That you don't want to do that? So then write to the code committee that your method is unnecessary that way. And this is correct. Your anger is my anger also. I am also angry. Why to do this? You want to ensure that your building should not collapse at MC. First of all, you do not design for MC. You design for DB. Why? If you want building should not collapse for MC,
no,
design should be MC.
That DBMC.
Achha, you are not angry on that. I was angry on that.
That DBMC is another part. That DBMC is another part.
So वो भी तो confusion है ना भाई.
वो है, लेकिन that is based on the probability, and that probability.
अरे इसमें भी based on probability तो और खराब चीज़ है.
तो उस पर हम रिलाई नहीं कर सकते.
रिलाई नहीं कर सकते. तो और गड़बड़ है. तो वहाँ भी गड़बड़ है. तो पहले तो MC से DB किया, फिर DB पे रेस्पॉन्स रिडक्शन फैक्टर लगाया, फिर उसको 1.5 से मल्टीप्लाई करके ऊपर उठाया, ठीक है, फिर उसको ओवर स्ट्रेंथ फैक्टर लगाया, फिर उसका एक कैपेसिटी कर्व बनाया. तो ये सब क्यों? सीधे क्यों नहीं MC के लिए डिजाइन कर देते और बाकी फैक्टर्स की जरूरत ही नहीं है. सो दैट्स व्हाई दिस सेमेस्टर. इस सब गुस्से का नतीजा है ये सब पढ़ना पड़ा. तो खाली गुस्सा करने से नहीं होता, उससे आगे भी करना. मैं भी गुस्सा हूँ. ये सब क्या क्या तमाशा है? पहले डिवाइड किया, फिर मल्टीप्लाई किया, फिर डिवाइड किया, फिर मल्टीप्लाई किया. ये सब क्या चल रहा है? ओके, but you understand what is what. You know what is R.
Yes.
You know what is omega.
Yes.
Okay, and you also know what is load factor. That was all.
We know it.
But you are not happy with it. That I agree. You should not be happy with this. Nobody should be happy with this. Only those people who have been told to do like this and they do it like this, only they can be happy. If a person is thinking why, then he will be unhappy. Code tells divided by 2, you have divided and you are happy. Then code says multiply by 1.5, you multiply by that and you are happy. That means you are not applying your mind. Why to divide, why to multiply, why this is going on? So, if you are unhappy, means you are thinking, it's good. But once you are unhappy, take the next step also. What will be the next step? To remove all this. So when you have to clean all this mesh, you have to go to performance.
Sir,
Yes.
in incremental dynamic analysis, how selection of ground motion is to be done?
Acceleration of ground motion is to be.
Selection of ground motion is to be done.
That was the topic, in fact, which I wanted to take today, but I got diverted with those questions. So this is the topic. So in nonlinear time history analysis, you need ground motion. So there are three sources of ground motion. One is recorded ground motion. Then we have synthetic ground motion, and we have artificial. So, as the name suggests, recorded ground motions are those which have been recorded during past time. Okay, and world over there are different agencies. In fact, in every country there is an agency which has this task to record and keep the ground motions and to make available to people who want to use those. In our country, which agency is doing this? IMD. Okay, so all the ground motions are kept by IMD. If any earthquake which has occurred in India, you want to get its time history, okay, its record, you have to approach IMD. IMD will provide you the details. Okay. In US, which is the agency? USGS, United States Geological Survey. Okay, the most reliable agency over the world, where you will get, even if an earthquake occurs in India, you could look to USGS website. They can provide, because they have a huge network, very large network. Okay. Like that, there are agencies in different countries. They are recording and keeping those records safe and also making it available to the people. Okay. So then there are some websites, some institutes which compile those ground motions, recorded ground motions, clean them, classify them based on different criteria, and then make those available on websites. Okay. So PF, NGA Best 2, those are the, like another we have Japan, Kicknet. So these are the, we have given you already a list in one of the assignment, one of the PPT. There is a list of different websites where you can find the recorded ground motion. Okay. So all the recorded ground motions you can get from them. If you do not have the recorded ground motions, there are procedures to synthesize ground motions. Okay. And we can also generate ground motions artificially. What is the difference? That we will come slightly later when we will see that recorded ground motion, which ground motion I should use. So we will first take that question. So which ground motion I should use? There are so many ground motions. Okay. Which ground motion I should use? So what do you think? A lot of ground motions are available on different websites. Thousands. Which one you will search? How you will search? Which one you will take?
We know the time period of our building.
You know time period of our building.
We select the ground motions, we plot the Fourier spectrum.
Okay.
And the frequencies from which our building frequencies are matching, that we will select.
Okay. So we will take those ground motions in which the predominant frequency is matching with our building. Okay.
Time periods.
Building period. That is okay, but that may be too conservative in some cases. Suppose my building, I am constructing a tall building. its period is 4 seconds. It is constructed on rock. So time period I will get, ground motions I will get, which is having predominant frequency in that range, 4 seconds, cannot occur on rock. That can occur on soft soil. So will it be advisable to take that?
We have to consider again your ground parameters.
So we have to consider the site conditions.
Right.
Okay. Which site conditions I should consider?
Whether the soil is rocky, alluvial, in river basin or in the area.
So when we are selecting the ground motions, first of all, we have to have a target response spectrum. Corresponding to which response spectrum? Response spectrum from where I will get? I will get from my site. So what type of response spectrum I am expecting at my site? Okay. That you can do a site specific hazard analysis, or you can just use from the code. So it can come from code or site specific hazard analysis. From the code it will come from a zone and just the type of the soil. Okay. Then the second parameter which I have to keep in mind is the magnitude of the earth. Magnitude of earthquake decides two things. One is the frequency content and another is duration of earthquake. Duration of earthquake depends on magnitude. Okay? And the frequency content also depends on magnitude. In addition to magnitude, these characteristics also depend on distance. Source to site distance. So the source which is governing my site, earthquake at my site, suppose that is a 10 kilometer, and I take an earthquake record of an earthquake which has been recorded at 100 kilometer. Okay, that is not justified. That will be different than what I am expecting at my site. So the distance also controls the duration and frequency. So frequency constitution and the duration depends on the distance also. So in short, both of these we call MR pair. So we have to decide MR pair, magnitude and distance. Magnitude and distance always go together. At what distance, what magnitude. And the last one is site class, and sometimes, although it is not used yet, but site period is also involved. Site class is based on VS30. So I should know VS30 at that site. And site period depends on the depth of soil. Actually, spectral shape depends a lot on this. Now, considering all these parameters, I have to select the ground. Problem is, considering all these parameters, you don't get ground motions which satisfy it. We have thousands of ground motions, but still those are not adequate that you will get ground motions matching with all your criteria. So what we have to do in that case, if it is not matching, we do scaling. We allow scaling. Okay, so scaling means what? If we are doing scaling, means that ground motion has been either recorded at a distance larger than my distance, or it has been recorded at a smaller earthquake, or vice versa. Okay. Then only, so the response spectrum of the ground motion is below or above. Let us say my target response spectrum is this. The ground motion has response spectrum. So what I have to do? I have to scale it up. Or if the ground motion response spectrum is, let's say, here, I have to scale it down. So I have to do scaling. But when we are doing this scaling, okay, the ground motion, if I need scaling, it means that ground motion is not coming from a similar source which is causing at my site and a similar type of site. There is some disturbance. So to some extent we can do that, but a scaling factor of more than 4 is not allowed. It should be less than 4. If you are doing scaling more than 4 times, okay, means there is a small earthquake, you are scaling it to MC, which is not correct. The characteristics of an earthquake of MC level will be different than the earthquake of lower intensity. Okay. So we have to select this. Now within this scaling also, we do not get the response spectrum which are close to my target response spectrum. In that case, what we do? We do what we call spectral matching. In scaling, we are doing what we call amplitude scaling. We also call it amplitude scaling. So here we are not changing the frequency content. Frequency content remains same. We multiply all the frequencies by the same factor. We scale all the frequencies by same factor. But in spectral matching, we modify the frequencies and we also call it frequency domain scaling. So the frequency content of the recorded accelerogram is different than my response spectrum. But I modify that so that the response spectrum comes closer. So we modify this and bring it close to my response. This is spectral matching. Naturally, scaling, spectral matching are making your recorded earthquake distorted. These are unnatural. Real earthquake was not like that. But I have pushed here, pulled here, and then brought it to my response spectrum. Because I am not having any other option. Ideal thing would have been that if I would have selected recorded earthquakes, and those earthquakes I would have got close to my response spectrum. That would have been ideal condition. But that condition, that those earthquakes are not there, that despite having thousands of earthquakes, we are not getting adequate number of earthquakes which can match all requirements. Okay, so we have to do this. When even this is not possible, okay, we can go for synthetic or artificial ground motions. In artificial ground motion, what we do? We do not consider any recorded earthquake. Randomly, we select harmonics and match and mix those harmonics in such a way that we get this response. Okay. So that is synthetic. Sorry, that is artificial. In synthetic ground motion, we do physics-based analysis. Let us say I have a source at a distance of 10 km at my site. I can make a finite element model of the whole thing, and then I can model the fault at this point, and for 10 kilometers that will travel, and then what I am going to get here. So this would have been ideal, but our analytical methods, numerical methods are not that efficient that we can simulate the whole of this 10 or 20 kilometer earth, okay, with all its properties. So there are errors, there are problems with this. Okay, so we either ideally take recorded, and if recorded are not matching with our requirement, we do some spectral matching. Okay, but spectral matching is not a desirable action. We do it only when we are forced to do it. We do not get recorded ground motion. We prefer to use recorded ground motion. And when those who are in PhD, they will be writing papers. The most common review comment you will get is how you have selected your ground motion, and because they know you can't get those ground motions, so those reviewers also know, and they will catch you there itself. Okay, so you have to be careful in selecting the ground motion, and whatever you are doing, okay, you should have a justification why you are doing that. So when you are writing a paper, be clear about which ground motions you have used and why. Otherwise, this review comment will always be there, because this is the most tricky part of whole of this time history analysis. Okay, one is simulation of different plastic hinges. That is one complex part. Another one is selection of ground motion. Okay, clear? Any question?
Sir, ultimate aim of the selecting ground motion is to get the response of the structure when earthquake is happening. And for that we are first doing is target response spectrum, which we are using from the code.
Not from core, maybe site specific, maybe core. Not always from core.
Not always from code, but whatever we are doing, like EPJ calculation, that we are using here. From there also we are getting demand. Then why we are again scaling up that or reducing up that one?
Because that demand is in the form of response spectrum, and I want to do time history analysis. And I told you that,
But to get that response spectra, I have also selected one earthquake data from which I get that one response spectra.
no, you have done when you are doing site specific analysis, you are not considering any earthquake data. You are not considering. If you were knowing from which earthquakes this response spectrum has come, which ground motion this response spectrum has come, if you know that, then use those ground motions. That will be wonderful. But those ground motions are not there. So what is given in the code, or what you are doing in site specific analysis, you are not obtaining from ground motions. Okay, you are obtaining using some indirect methods.
So whatever the given in the code, we use it just as a data point. And from that,
In fact, if you try to search the ground motion, which can give you the response spectrum given in the code, it is not possible, because the response spectrum given in code is totally artificial. Okay, it is an envelope. No earthquake can generate that type of response. So that is the problem. That's why first we decide response spectrum, and then we look for ground motions which are close to that response. I want to tell you only this, although there is a lot of things in this. Course can be on this, how we should select ground motion, how to do the scaling, what are the different scaling methods. But fortunately that is not in your scale. So you should be happy. Those who are unhappy can read first ASC 7. Okay, the first document is ASC 7, which talks about how we can do the selection and scaling of ground motion. Okay. Then you have to also learn PSHA, probabilistic seismic hazard assessment, to know the characteristics of your site, which earthquake. Suppose you have selected a site in India. So that site, which type of sources are governing that site? All that information you need to know. So that you can get from PSHA, and there is a software, public domain software, OpenQuake. That is very useful. In open quake, they have implemented all the sources available at that time, all the sources for it. So that is available, all that information is there in public domain, and it will be very useful for you while you will be selecting ground. So any question? Any
So if it is response spectrum given in the code is you are saying that is artificial and it is ignorant. Then for idealized condition, why you are comparing whatever the dimension you are getting with that one?
Because we do not have better option than that. If you have better option than that, you can have. But for that you have to do site-specific analysis. If you are not doing that site-specific analysis, you do not have better, then you have to do it. Whatever you cover. But if you can get better, you can. Okay. So can we move to the next topic now?
So why this spectral matching is not reliable?
Why?
This spectral matching is not reliable.
Because you are changing the frequency content of a natural earthquake. Okay. That means you are making it unnatural. That type of earthquake which will result after this spectral matching is not a natural earthquake, because that has not occurred anyway.
Yes, sir. But,
So if it is unnatural, means that type of earthquake cannot occur at my site also.
that is unnatural for that source.
No. For the same response spectrum, you can have n number of solutions. It is not that one earthquake will give one response spectrum. Okay. Several earthquakes can give you same response. Okay. Now which one you will take? Some of those will be totally absurd, artificial. Some of those will be natural, close to natural. So you want to take those solutions which can occur in nature. Okay. So far we do not understand this process so well that we can, by looking at the accelerogram, we can tell that this can occur in this situation, this cannot. Okay. Slowly, when our understanding will improve, then we will be able to tell that natural earthquake occurring in this condition will look like this. Still we do not have reached that stage. So what we are doing till we have not reached that stage, we take those earthquakes which have naturally occurred. If I am taking an earthquake which has naturally occurred and it is also matching with my response spectrum, nobody can question. But if I am using another earthquake which is matching with my response spectrum but it has not occurred, then I have to prove that this is a natural earthquake, this can occur. That's the problem.
So one more thing.
Yeah.
In this amplitude scaling, are we changing the frequency distribution?
No. We are just changing amplitude.
So the frequency distribution is what is the amplitude with respect to the
Right.
particular frequency.
Right. So it will be simply scaled up. You can make it double, but the shape will remain same.
The shape will be
It will be simply scaled. So frequency content will remain same. Amplitudes will, suppose you do Fourier transform. So your ground motion will do Fourier transform A0 plus A1 sin omega t plus phi. Okay. And then multiply this A0 and omega by a factor of let us say C. What will be the change in the Fourier spectrum? Just amplitudes will be multiplied by that factor. That's it. So that's what we are doing in amplitude scale.
So frequency distribution is the shape of that spectrum.
Right. Which are the frequencies which are contributing more and which are the frequencies which are contributing less. So that relative contribution of different frequencies, that will remain same. Absolute contribution will increase, but relative contribution will remain same. Okay, so all this which we have discussed so far in today's class is of the syllabus. Okay, but just to give you an idea where you should look in future, what is beyond that I have discussed. So let's go back to what is in your syllabus. and that is liquid retaining structure. What are the liquid retaining structures which we structural engineers commonly deal with? Water tanks, what else? Dams. Anything else? Oil tank or water tank? Liquid. Sorry, nuclear power plant. Nuclear power plant where you are getting water. Liquid is there, but that liquid will go to some tank now. Tank we have already used. In Roorkee, what is the most important structure? Canal, but canal is whole starting from Ganga to Ganj. But what is the structure, main structure which is landmark of Roorkee? Aqueduct. So that is also a water retaining structure.
Is it a retaining structure?
It is retaining. In aqueduct, okay, what you are doing? If suppose you do not retain the water, what will happen? It will flow in Solani river. So you are retaining it from flowing into Solani river. Otherwise it will flow in Solani river. So it is also retaining, and when earthquake will come, similar effects will be on all the three. Okay. Due to this water, similar effects will be there on all the three. So let's see in water tank. So water tanks you have above ground water tanks. The simplest one, our above ground water tank. We can have, these are called ground supported or above ground. We can also call ground support. Then we can have underground. We can have ground water tank underground, and we can have overhead water. Overhead water tanks are in different shapes. Maybe rectangular, maybe circular, maybe conical. Okay. And there is a very typical shape . There is a beam running here, there is a beam running here. Anybody who remembers what are these tanks called? Ends tanks. JE or JET? I don't know. What is the advantage of these indus tanks? Why this shape is preferred? Here, if you see, there will be water pressure. This water pressure will also be at the base. And this is also equal to weight of water. You know. So, this surface here, the slab at the bottom, this will be subjected to bending moment. Okay. You can reduce this bending moment if you make this in the form of a dome. So circular water tank you can make in the form of a dome. When this pressure will act, what will happen? What is the advantage of having a dome? All of you know, same as having a beam and an arch. So what is the difference? It will reduce bending moment and transfer that bending moment as compressive force. So when this compressive force is transferred here, you can see that there is a vertical component and there is also a horizontal component. So it will apply a hook tension in this ring beam. So this ring beam will be subjected to hook tension. And you know, RCC is not very good in resisting tension. So we should avoid tension as far as possible. So this hook tension in this ring beam, that becomes a critical design issue. You can reduce this if you counterbalance that tension, that compressive force which is coming from here with this conical. This part is conical. Okay, here it is dome in instant. So these two components balance, counterbalance it. Okay, so whatever force is coming here, okay, that will get counterbalanced from the process. Still, because of this pressure, hydrostatic pressure, there will be tension, but that tension can be reduced. So this shape, in this shape, we reduce tension to a large extent. That's why this is preferred. Okay. Then water tanks can be supported on the frame structure. This is called staging. Overhead water tanks can be supported either on staging. Staging is nothing but beam column frame. Different shapes of beam column frame you might have seen. Okay. Just behind Kasturba, near to NCD guest house, you can see there is a water tank. It is on staging. So some beam column frames are there. So it can be supported on staging, or it can be supported on shear wall frame. This is called shaft. So a circular cylindrical shear wall may be there. We call that as shaft. And you can find different types of beautiful shapes of water tanks, like one water tower. Okay, so this is
shear wall can be circular. it is circle, then all side it has equal area.
All side is
All the direction it has equal amount of direction, and whatever the shear area it has to apply is equal.
Right.
And
then
how it is shear?
okay, you want to call it some different name, so call it shaft. If you are not happy with shear wall, do not call it shear wall, call it shaft. But when I said shear wall, I mean a concrete RCC wall. Okay, so RCC wall, a concrete wall which is constructed in circular fashion. Okay, so actually it will act like a shaft. So it is basically a shaft. A flat shell. Have you heard about flat shell? Have you heard about flat arch? Have you seen a flat arch? I can suggest you a very wonderful picnic place. Okay, that is Forest Research Institute, Dehradun. Go to Forest Research Institute, Dehradun. It's wonderful. But look at their building also. They have a massive masonry building and different types of arches, masonry arches you will see there. And you can see their flat arches. Okay. So what is a flat arch? Name suggests it is flat. Okay. But its principle of action is same as that of arch. It is not developing tension. Okay. So I leave you for thinking how it is possible to have a flat member which is not having tension. How the load transfer takes place there. So on similar lines we can have a flat shell. So flat shell is shear wall, and when the shell is curved, it is shaft. So the same RCC wall in the curved manner, when we construct it, we call it shaft. Now let us look at what will happen to these different types of tanks during earthquake. Let's take first this one. What is going to happen? You might have seen some of the videos in the past earthquakes where tanks were at the top of the building, and during earthquake, what was happening? I wish I was having those videos here. I have. Okay, maybe in the next class tomorrow I will show you. What do you think? What will happen? If you have a tank, okay, and it is subject to shake, what is going to happen? What is हाइड्रोडायनामिक्स तो बहुत आगे की बात है. होगा क्या? What is going to happen? You think it like this. In one case it is filled with water, in another case it is filled with soil to same height. What would be the difference? Will it be same? If you have soil and you are shaking, and if you have water and you are shaking, will the behavior be same? What difference you think? What you can visualize? Forget about earthquake engineering, structural engineering, everything. Your common sense. What you are expecting? What will happen?
All the particles of the soil will move in a rigid manner.
So soil will move in a rigid manner. It will behave as it is part of this tank. So it will not have any relative motion. It will move along with the tank. So what will happen in case of water?
In case of water will try to up and down. And due to that, shear stress will change on the.
So there is a phenomenon, what we call sloshing. Water will go like this and this. When you are moving in this direction, the water will go in this direction. When it is moving in this direction, water will go in this direction. And as a result, the water spills from it. You might have seen in those videos where water tanks were at the top. And usually when earthquake has stopped, after that, the water starts falling from there. Okay. So this water will have sloshing. Now do another thought experiment. In one case I have a water tank like this. And another case I have a water tank like this. Both are. What do you think? Will the behavior be same? What difference is there? What will happen in case of the shallow tank? And what will happen in case of this deep tank? Sloshing will be more here. And here? Here. स्विमिंग पूल वाला है क्या?
उसमें क्यों हुआ?
लेकिन ये कैसे करेगा?
इसको नहीं उसको समझ नहीं
इंटरनेट है?
हाँ हाँ दोनों को हाँ है करंट
अच्छा एक और था जिसमें हाँ शायद देखते हैं We forgot swimming pool is also water treatment structure. Okay, you can look at this one. Look at this. What is happening? It is what? It is shaking now. The camera is shaking. Why people are running? Nothing was happening there because earthquake vibrations were already there. People have sensed that earthquake was there. Water is sloshing later. So in one of the earthquake you have seen, it was, and you see how the water is. Lucky that building did not collapse. हाँ, और कौन सा दिक्कत?
Top of the building.
वो वाला, ये वाला नहीं। It is the same, but another video. This is longer duration. Look carefully water. Water is still. Photo is vibrating. You can see no movement in water, but the photo is vibrating. And it is shaking heavily. Now you see, photo movement has stopped. And water is vibrating. Photo movement is slowed down. So what was happening here? The camera was connected to the building on a rod. So initially, when earthquake was vibrating, earthquake came, initially it was the camera which was vibrating. There was no movement in the swimming pool. The camera was vibrating, and due to that, the photo was vibrating. Then the camera stopped, and water started vibrating. What does that mean? Initially, the ground motion was having higher frequencies. Those frequencies were matching with the frequency of vibration of the camera. That's why you at one stage, the photograph has shaken so much. It looked like the camera has fallen or something. It has not fallen, but the vibrations were so much because those higher frequencies were matching with the frequency of the camera mounted on a rod. So if a camera is mounted on a rod, its frequency will be very high. So initially the earthquake frequencies matched with that, and then after some time those higher frequency waves have stopped and low frequency waves come to either surface waves or the motion comes again. After making a round, it comes again. So then those frequencies match with the frequency of the water. So what it suggests is that in the sloshing motion, the frequency is very, very low. That matches with the low frequencies of the earthquake which occur when the main strong motion has passed. After that there is a slow motion. There is a low frequency and low intensity wave. But that frequency is matching with that of the water, sloshing water. And then you saw a lot of movement of the sloshing water. So one thing is that in the sloshing action, the period is longer, the frequency is low. Secondly, you saw that lot of water is coming out. Okay, so the amplitude is much larger and it takes lot of time. Once this water starts sloshing, it takes lot of time to become stable. Okay, so damping is very good. So in water, you can see the damping is good. What do you think about this? Let me extend this further. Suppose this is just a tube and I fill it water. What will happen? Will there be sloshing? If I fill water in a tube and shake it, will there be sloshing? No. So, sloshing occurs in shallow water or in the top portion of the water. Whereas in the lower portion or in the deep tanks, water behaves in the same way as soil. That means it is connected to the walls of the water tank. So in our water tank, there will be a portion of the water below, okay, which we call impulsive water or impulsive component of the water mass, MI. And at the top we have convective. So this convective mass MC, this is doing sloshing. This is vibrating with respect to the walls of the water tank. Whereas this impulsive mass is behaving as if it is attached. Sorry. As if it is rigidly connected to the walls of the water. Okay. What will happen here? Here also there will be impulsive and convective component, and what we do, we connect the impulsive part MI rigidly with the wall, and this convective mass MC is connected through this space KC, and this is higher. This height we call HC and this height we call HM. Behavior of the water will be same, but on the wall there will be soil pressure also. That will be the difference. Otherwise, whether your water tank is on the ground or below the ground, the behavior is going to be the same. Now you can imagine what is going to happen in case of overhead water tank like this one. In addition to those motions, impulsive and convective, the water tank itself will vibrate. Okay, it is like a inverted pendulum. So this inverted pendulum will start vibrating, and the impulsive mass will vibrate along with the water tank, and convective mass will vibrate with respect to the water tank, related to water tank. So we can make the same two mass model here also. We call it two mass model, where impulsive mass we connect to rigidly and convective mass we connect to viscous. So model of an overhead water tank. This is impulsive mass plus mass of the water tank. Let me not use W because W may confuse with water. So I am writing MS structure. So mass of the structure itself plus Mi, okay, and this stiffness will come from staging Ks. Okay, and this is Mc, and this is Kc. And actually the period of vibration of the water tank and the period of vibration of the convective mass will be quite different, and if these are different, we can use superposition method. Okay, so we analyze two structures. One is this Mi plus two single degree freedom system, Mi plus Ms having stiffness Kc, and another one this Mc having a stiffness Kc. Okay, so what you have to find out is the value of Mc, Kc, Mi, their heights from here. Okay, the height of the water is h. These are all available in IS 1893. We have already given you the copies of IS 1893 part 1. If not, I have here. You can copy those. Right and allowed. So look at this code. For these values, how to obtain Mi, Ms, Mc, the stiffnesses. Okay. So how do we obtain this? All this is explained in IS 1893. We go through that, and when we meet tomorrow, we will take up. This is sorry.
Series connection between these two masses.
So if delta is different, is parallel or series?
Series.
Displacement is different. So it is series. So here also it is series. So the forces which will be acting here and which will be acting here will not be in phase. So when peak of this will occur, peak of this may not occur. So we will combine them using S analysis.